Hi, in this video I'm going to be solving a problem in which a charged particle feels a force from two other charges, but they're all in one dimension, they're all on a line. We're also going to talk about a few other things related to the forces between all three particles, but let's just get started. Three charges are on the y=0 line of the coordinate plane. I'm going to zoom in here. The first is 2.00 millicoulombs at x equals 0.00 meters. The second is negative 4.50 millicoulombs at x equals 5.00 meters. The third is at negative 3.00 millicoulombs at x equals 1.50 meters. Find, A, we need to sketch a diagram of the charges. B, we're going to have to draw free body diagrams for the charges. C, we need to find the magnitudes and directions of the forces on charge 2. And then D, we need to find the magnitude and direction of the net force on charge 2. So let's just start with A. Let's sketch out a diagram. Everything's on the y=0 line, so I can just, that's the same as everything being on the x-axis, so I'm just going to have a little x-axis right here. And we have a positive charge of 2 millicoulombs at x equals 0. I'm just going to label that. Q1 equals 2.00 millicoulombs. And the position is going to be x equals 0. The next charge is at x equals 0.5, and it is negative 4.50 millicoulombs. I'm just going to put this right here. Use blue for negative. Q2 equals negative 4.50 millicoulombs, and it is at x equals 0.500 meters. And our third charge is negative 3.00 millicoulombs at x equals 1.5. So it's going to be pretty far out. Q3 equals negative 3.00 millicoulombs, and the position is x equals 1.50 meters. So here's our little diagram of our charges. Next we need to draw free body diagrams for each of the three charges and identify the direction of the force with a subscript. So let's just start with charge 1. I'm going to do the free body diagram in, let's just keep it in red. Well, it's going to feel a force from both Q2 and Q3. So it's going to feel a rightward force from Q2. So we call that F on 1 from 2, or F1, comma 2. It's also going to feel a rightward force from Q3. So we can label that F on 1 from 3. And we don't know the sizes of those vector arrows, although actually Q3 is definitely going to be, or the force on 1 from 3 is going to be smaller than the force on 1 from 2 because it's a smaller charge and it's farther away. Let's look at the forces on Q2. Well, since it's a negative charge, it's going to feel an attractive force from Q1, the positive charge, and a repulsive force from the like charge, the negative charge Q3. So it'll feel a leftward force. I'm running out of space, so I'll just do it up here. The force on 2 from 1 because it's attractive, and it's repelled from Q3, so that's also going to be a leftward force. The force on 2 from 3. Two leftward forces there. Q3, let's see, Q3, well, Q3 is going to be attracted to the positive charge, so it's going to feel a leftward force from Q1. Whoops. The force on 3 from 1. But it's going to be repelled by that negative charge Q2. So it's going to feel a rightward force from Q2. The force on 3 from 2. So those are our free body diagrams. That covers part B. Now we can do part C. We want to find the magnitude and direction of the forces on charge 2. Now charge 2 is right here. We only have two forces, the force on 2 from 1 and the force on 2 from 3. So let's just calculate those forces. We know all of our forces obey, or electrical forces obey Coulomb's law. F equals negative K Q1 Q2 over R squared. So let's just look at the force on 2 from 1. Force on 2 from 1 is equal to, did I add a negative sign there? Let's get rid of that negative sign in Coulomb's law. That's unnecessary. Force on 2 from 1 is equal to K, which is 9 times 10 to the 9 newtons meters squared per coulomb squared. Q1, which is the first charge, and in this case, since we're looking at charges 2 and charge 1, I'm going to make Q1 actual charge 1. So let's make that 2.00 since it's millicoulombs times 10 to the minus 3 coulombs. Our other charge, Q2, is negative 4.50 times 10 to the minus 3 coulombs. I'm omitting units, that's because I'm keeping everything in base SI. Our answer should be in units of force if everything's in our regular SI units. And R is the distance between these two charges. Well, that distance is going to be, well, from Q1 to Q2, it's just 0.500 meters. So we plug in 0.500 meters, and it's that distance squared. Then we just plug it into our calculator. We do 9 times 10 to the 9 times 2 times 10 to the minus 3 times negative 4.5 times 10 to the minus 3 divided by 0.5 squared. Whew, that's a lot of force. The magnitude of our force is going to be, it's going to be 324 kilonewtons, or let's write it in scientific notation. Negative 3.24 times 10 to the 5, and the units are going to be newtons. That negative sign just tells us that it's an attractive force, but we already know that. So we could also write this as 3.24 times 10 to the 5 newtons. And we already know it's pointing to the left. Now let's find the force on 2 from 3. So the force on 2 from 3 is just going to be equal to Coulomb constant times charge 2 times charge 3 divided by the distance between 2 and 3 squared. That's going to be 9 times 10 to the 9 times charge 2 is negative 4.50 times 10 to the minus 3. Charge 3 is negative 3.00 times 10 to the minus 3 divided by our distance between Q2 and Q3, which is, well, it's between 0.5 and 1.5, so our distance is just 1.00 meters all squared. I'll label that in the diagram as well. This is 1.00 meters. So we plug that into our calculator, and we simply get 9 times 10 to the 9 times negative 4.5 times 10 to the minus 3 times negative 3 times 10 to the minus 3 divided by 1 squared. 1.22 to 2 sig figs times 10 to the 5 newtons. And another way of writing that, since we already know the direction, it's going to be 1.22 times 10 to the 5 newtons. We know it's pointing to the left, so it's left. It's going to be our answer to C. And last of all, if we go back, part D asks for the net force on charge 2. Well, the net force is just the vector sum of all the forces. We know all of the forces acting on charge 2. We just solved for both of them. So since we have a leftward force and a leftward force, the magnitude of our net force is going to be a larger number, and it's going to be pointing to the left. So we're just going to add these two vectors up. 3.24 times 10 to the 5 newtons plus 1.22 times 10 to the 5 newtons. And the magnitude of that is 4.46 times 10 to the 5 newtons. And since we have left and left, the direction is going to be to the left. That's all. One quick little caveat here. Well, it's not a caveat. But our forces were both in the same direction. They were both pointing to the left. If, for example, force on 2 from 3 were rightward pointing, then we would have to make one of these negative, because those forces are going to partially cancel. We have a leftward force and a rightward force. We have to choose one to be positive and one to be negative. It doesn't really matter. We just have to be consistent. That wasn't an issue in this problem, but it may come up in other problems. Well, I hope that's helpful. That's the electric force from two charges along a line. Bye.